Welcome to today's Explainer. If you're looking to modernize your infrastructure deployment pipelines, and let's be real, who isn't, you're in exactly the right place. Today, we're unpacking a really robust, production-ready GitOps foundation for provisioning AWS infrastructure. We'll be using Terraform and GitHub Actions. And the best part, we're going to see exactly how to secure your delivery without ever, for sure, relying on static, stored keys. So think about this for a second. What if you never had to store an AWS secret key in GitHub again? For years, the standard way to deploy infrastructure meant taking your long-lived AWS credentials, your access key ID and secret access key, and just storing them as variables right in your repository. It's honestly a massive security risk. I mean, if those keys leak, your entire infrastructure is completely compromised. So what if we just eliminate that risk entirely? What if you never had to hand over the master keys to the building just to make a quick delivery? Well, the answer here is OpenID Connect, or OIDC for short. Instead of relying on static keys, GitHub Actions uses OIDC to grab short-lived, temporary AWS credentials. You can think of it kind of like a highly restricted VIP pass. The system issues a pass that's only good for one specific person to enter one specific room for a very short amount of time. And once the job is done, poof, the pass vanishes. Absolutely no static keys are ever stored in your repository. It's a total game changer. Okay, here is our roadmap for today. First, we'll look at the OIDC trust architecture. Second, protecting Terraform state. Third, CI/CD delivery workflows. And fourth, smart recovery and security. Let's get right into it. Section 1, the OIDC trust architecture. Let's ground ourselves with a bird's eye view of a commit's journey. It all kicks off when a developer opens a pull request, right? That triggers GitHub Actions, which spins up environment-specific jobs. Now here is where the magic actually happens. Instead of grabbing some saved password, GitHub requests a signed OIDC token. AWS STS, the security token service, steps in and validates that token through the IAM OIDC provider. Once it's verified, the job assumes a highly restricted IAM role, interacts with a remote Terraform state, and eventually pushes those approved changes out sequentially. Dev, then staging, then production, all while a read-only monitor keeps a close eye on state locks. So how does that trust boundary actually function in practice? Well, when the GitHub runner needs access, it gets an OIDC ID token, which is basically a signed JSON Web Token, or JWT. AWS STS will only accept this request when two very specific conditions are met. First up, the audience claim. The OD has to strictly be sts.amazonwebservices.com. Second, the subject claim, or sub, must explicitly match your exact repository and the specific GitHub environment making the request, like dev or prod. It creates an incredibly tight security perimeter around your infrastructure. And that brings us to a really core concept. Every single environment role in this architecture features two completely independent layers of protection. First, we have trust isolation. Like we just talked about, AWS only accepts tokens from the expected repository and the specific GitHub environment. But let's say someone somehow got past that. We still have permission isolation. The temporary credentials that get generated inherit only the permissions of that specific role, strictly limited to precise state prefixes and environment namespaces. It's basically like wearing a belt and suspenders. When you map out the environments, you'll notice how the development environment role maps directly to the environment.dev suffix and is physically restricted to the n/dev/terraform.tf state key. The production role, it has entirely different, totally isolated mappings. Because of the strict least privilege IAM setup, the code running in your dev environment literally lacks the permissions to ever accidentally read, write, or overwrite your production infrastructure state. They are completely 100% fenced off from one another. Moving right along to Section 2, protecting Terraform state. To make this whole GitOps foundation work securely, we need to deploy a specific set of AWS resources, and each one comes with strict controls. The IAM OIDC provider establishes GitHub as a federated identity provider. Then we have our isolated environment IAM roles. But crucially for Terraform, we rely on an Amazon S3 state bucket and an Amazon DynamoDB table. And guys, these aren't just vanilla out-of-the-box setups. They are heavily restricted to protect your infrastructure's absolute source of truth. So that S3 bucket acts as your shared Terraform backend. It's locked down with versioning-enabled, AES-256 encryption, and a strict public access block. On top of that, we use a DynamoDB table with a lock ID partition key. Why DynamoDB? Because it handles state locking. It physically prevents two concurrent Terraform processes from trying to write to the state file at the exact same time. If they did, it would corrupt your entire infrastructure. So this is a mandatory physical barrier protecting your data. Let's jump into Section 3, CI/CD delivery workflows. The workflow starts with a pull request plan. When a developer opens a PR, a workflow fires off that assumes the correct IAM role via OIDC and initializes that secure S3 backend we just talked about. It formats the code, validates it, and creates a Terraform plan. But here's the really brilliant part. It takes that plan, converts it to JSON, and runs an AI-assisted plan reviewer against it. Before a human even lays eyes on the PR, this AI agent is already highlighting deletions, replacements, and any sensitive security changes, dropping a risk assessment directly into the pull request. It's incredibly smart.
Now, once that code merges to the main branch, the system doesn't just blast those changes everywhere all at once. It applies them sequentially. First, it goes to the isolated dev environment. If that's successful, it moves on to staging. Then, and this is a critical security boundary, it hits pause. Deploying to the production environment requires a strict human-in-the-loop approval gate within GitHub environments. It's only after a required human reviewer officially signs off that the production deployment actually proceeds.
Finally, Section 4, Smart Recovery and Security. Enter the Lock Doctor. This is an automated workflow that runs every 30 minutes, as well as after every single plan or apply. It correlates lock age with workflow activity to diagnose any stale locks, but notice the key phrase here, read only. The Lock Doctor assumes a monitor role with only DynamoDB get item permissions. It requests an AI-assisted assessment and opens up a GitHub issue, but it will never, ever automatically delete a lock or mutate your AWS state. That safety boundary remains perfectly intact. Because automated deletion is disabled by design, we rely on a human-approved remediation process. If a lock gets stuck, an operator first has to verify that no Terraform process is actually running in the background. Then, they manually trigger an unlock-approved workflow, putting in the specific environment and the lock ID. Crucially, doing this requires completing a GitHub environment approval. Only after a human authorizes it does the workflow execute the Terraform force unlock command, using the proper environment role. We really need to highlight a stark operational warning straight from the documentation here. Never force unlock state while another Terraform process is running. This is exactly why we require authorized human intervention. If you force unlock while another process is actively writing, those concurrent state modifications will corrupt your Terraform state. The friction built into this unlock process, it isn't a bug. It's an intentional, absolutely vital safety feature. So everything we've covered today makes up a robust foundation using a single AWS account. But as your enterprise grows, this architecture naturally evolves with you. The target state roadmap includes hardening your setup with customer-managed KMS keys and Security Hub. You can separate environments entirely into their own dedicated AWS organization accounts. Plus, you can observe everything using EventBridge and centralized logging and ensure smooth recovery with cross-region state replication. The beautiful thing is that the OIDC and GitOps foundation we've discussed scales perfectly into this mature target state. We've seen how combining GitHub OIDC with Terraform and sequential promotion completely eliminates the need for static keys. It physically separates your environments, and it ensures human oversight is injected precisely where it's needed most. The tools to build a fortress around your infrastructure are sitting right here. So the final question I want to leave you with today is this. Knowing the serious risks of stored credentials and concurrent state corruption, how will you secure your next deployment pipeline? Thanks so much for joining me on this explainer. Keep learning and keep building securely.